today we will discuss about the we have started the. Can you summarize? Anyone summarize what we discussed in the last class? I have already uploaded the presentation, but just a standing information to all of you that whatever I am teaching, okay, still now comes from the Gonzalez book of digital image processing. So whatever I teach, you can just get back to the book and learn it. Okay. So anyone wants to summarize what I discussed in the last class?
Sir, it
Mhm.
was the image sampling, quantization, then the types of image enhancement and the image enhancement operations.
Yeah, so we started discussing the spatial transformation, right? We started
Right.
discussing the spatial transformation, which may be point wise, which may be neighborhood, and which may be global.
Global.
Okay, so neighborhood is mostly called local, and is called global. We have just started the initial transformations. Today we will actually look into the transformations which is called filters. Okay, so what are filters? Any idea what do you mean by filters? I think in digital signal processing we discussed about filters. You can just take the same idea, only you need to change the sample, a special sample. Okay, so filters are systems, subsystems, okay, which can actually work on your data, right, and can selectively work on your data, which means that it works. Okay, that means it tries to um, if it tries to select some samples, okay, or process some samples, okay, compared to the other samples. Okay, it depends on the type of the filters and depends on the type of the sample. So filters have a selectivity for your samples. Okay, now what we try to discuss today is the samples in the spatial domain. So the filters which works on the samples on the spatial domains are called the spatial samples, right? And in the image, we can also have samples in the frequency domain. So image samples can be represented both in the spatial domain form as well as frequency domain form, right? So spatial domain form samples mean samples will have the pixel coordinates and will have the intensity values. Okay, and frequency representation of the spatial samples we will come maybe in the next class. We'll start it. Okay, so before that we will just try to finish this today's lecture on the spatial filtering. Okay, which will work on the spatial samples, which is also that is a type of filtering in the spatial domain of the image. Okay, so let me start. um, so can you all look into my can you see my presentation? Okay, good. So we all know this. So this is just a precursor to what we already discussed. So what is an origin? What is an image XY? What is the neighborhood of an image? We all know this in the last class on the spatial information discussion. We are just trying to this is a precursor. So okay, so a spatial filter is something which works on a neighborhood. Okay, it is either called filter, mask, kernel, template, window, whatever nomenclature are there. There are different several nomenclatures are there, but ultimately it's a matrix operation. Okay, which is done on the neighborhood. Okay, so a spatial filter marks is moved from point to point in an image. So when we try to apply this filter, what does it mean that applying this filter means that we are applying this filter on the spatial domain of the image. Okay, Let me again. So did you get my discussion? That was what I discussed with you in this discussion. Are you getting me? My slides are visible.
Yes, sir.
Okay.
Yes, sir.
So got this filter, right? So we operate this filter. Center of the filter mask, we tell this a filter mask. Center of the filter mask works on each of the fxy's of the input image and does an operation involving the neighborhood defined by the filter mask, and it replaces this fxy and creates a new pixel intensity value which comes as the output image as a gxy, and that's the way how the filtered image output is generated. Okay, this is the operation. I think you understand. That means you understood this operation, right? All of you. This is the input. This is the kernel mask, filter mask. And this is the output of the filter. Is it clear to all of you? Okay. So now the simple neighborhood operations can be mean and max. What is the mean? Set the pixel value to the minimum in the neighborhood. Set the pixel value to the maximum in the neighborhood. Okay. So this is the way how it works. This is a 3x3 neighborhood. Okay, original image pixels are A, B, C, D, and this center maps here. Okay, and then it operates. So this is the original image, and this is the filter wet. So when we tell the filter mask or what the filter consists of, filter consists of the wet. Is a 3x3. It will have the wets values, 9 wet values of the filter. Okay. So now what will happen is that this filter, suppose this filter is operating in this neighborhood, and so this is the center pixel of the, this is the pixel concerned which we want to, okay, that means on which this filter is operating. So what will happen? This will happen. So the new E, so the new value of the E will be summation of, okay, summation of n star E j star. Yes, the corresponding weights will we get will operate, right, or multiply with the corresponding pixel values in the neighborhood, and will generate a new, okay, a new E. Okay, and this is repeated for every pixel in the original image to generate the filter. Is okay. At one point of time, you can tell that, oh, sir, if I only do this, okay, this can cross the value of 255. So normally, then it's normalized. It's not just being multiplied and added like that. It's normally normalized by some constant coefficient. It may be 1/9. Okay, so what we do, we actually do this sum. The most common way of normalizing is that, okay, you do this sum and we divide this as a 9, because this is a 9 element value. So we try to okay, try to normalize this by 1/9. Okay, okay, right, and do it. Okay, so what I show here is basically the general process of applying the filters. Okay, any confusion any one of you have on this? Are you all clear? This is the filter mask. I'm setting an example of 3x3 filter mask. This is the example region of the image where the filter mask is applied, and this is the computation that we do at each pixel. Only the point is that we have to normalize it so that it doesn't goes over 255. Okay, in the spatial intensity value, and this will be performed for all the pixels. Okay, right, and for a particular filter, the filter mask will not change. If you are changing the filter, what is meant by I'm applying a new filter? I'm applying a new filter means I am changing the the width of the filter. Okay, and that's what is, okay, what is the filtering. Okay, so any confusion any one of you? Is it clear to all of you?
Yes, sir.
Right. Okay, so now we will go into some specific filters. One is called the low pass filter, one is called the high pass filter, as from your digital signal processing digital signal processing knowledge, you can understand that low pass filters means that the filters which passes those intensity points, okay, which are basically of low frequency. Low frequency means which doesn't changes in the neighborhood. A low frequency information in the case of image information is that if the neighborhood is almost the same as that of the pixel, okay, then it is called a low frequency region of the image, and a low pass filter will generate higher intensity on those regions of the image where the intensity doesn't change as much, and it will generate low values. Okay, low values means gxy will be low because gxy is the output image of the filter. So gxy will be, in the case of low pass filter, gxy will be low for the regions where there is a larger change in the neighborhood because it's a low pass filter, right? And the inverse case appears for the high pass filter. In the high pass filters, gxy value, the output image values, will be high where there is a change in information in the neighborhood in the input image, means in the fxy image. Okay, for the case of high pass filter, and for the case of high pass filter, gxy values will be low for those pixel regions of fxy input image where the pixel doesn't change as much. So it's just the inverse, high pass and low pass. Okay, so basically low pass filters are called smoothing filters, which means that it tries to make the regions, the neighborhood, all look similar. So neighborhood all look similar will be preferred in the low pass filter, and it will try to do that. So that makes that it is a smoothing. Smoothing means neighborhoods are all more or less same. It's smoothing filters. Okay, these are basically used to reduce noise inside the objects. Okay, because noise pixels inside the objects are, okay, are larger deviations from the region, okay, from the neighborhood. So if you can reduce the deviation with a low pass filter, okay, then the noise is reduced. Whereas in the case of high pass filters, they are called sharpening filters, which means that they actually enhance the differences in the neighborhood, and so it sharpens the image, which means that the edges are more well visible. Okay, uh, edges are more sharp because edges are the regions which have a sharp difference between its neighborhood, because due to that, as it is lying in the border, it will have different pixels from coming from different objects or different backgrounds. Okay, so this type of filters will actually make those gxy's high, those have a much difference from the neighborhood, so it will sharpen those edges, because edges are those fxy which has more difference among the pixels. Okay, so these are the two things, okay, we will study. Okay, so there are two, again out of these filters, low pass filter, there are two types of filters, two types of operations, actually not filters, I will say two types of operations. One operations is called linear, and one operations are called order statistics. Okay, it will soon get what does it mean. Okay, so as I say, okay, who can tell that if this is the, or you can just represent it by all ones and 1/9 in front, whatever is the case. Okay, can we appreciate that this is an averaging filter? Can we appreciate this is this mask which has 1/9 1/9, or you can also appreciate it as all ones in this matrix cells, and 1/9 in the like that in front. So it's 1/9 multiplied with all one matrix. Now if I do this operation on an image, okay, like this will generate an averaging filter. Is it yes or no? And if yes, why yes? Who can answer this?
Sir, yes, sir, it would be an averaging filter because like there are nine small cubes, and so it's like adding.
Yeah, it's basically one. So it what it means? It one means what? All these weights are one. What it
Yes,
means? It means you are just adding A, B, C, D, E, F, G, H, I,
yes, yes,
right? And you are dividing this with one with nine,
with
and
nine.
you are
Yes,
replacing this E with the value because
yes,
E
sir.
processed is this new E. Okay, what will be this center pixel of the in the image GXY will be the average value of all its neighborhood because you
Exactly,
are
sir.
just adding it and dividing it with nine. So it's average of the nine neighborhood pixels, and that value is replacing a center pixel. Okay, so in each of the GXY you do that. So each of the GXY is generated by doing this on the FXY. So each GXY is basically consisting of the average value of the neighborhood which was in the input image fxy, right? So
Yes, sir.
all of you can very easily get that this is an averaging filter. Okay, right? And this is called a linear operation because there is no nonlinearity in this particular process, right?
Yes,
This
sir.
is basically. Mhm. It will not call averaging filter, it will be called weighted average. Okay, that's the difference. Okay, it will be not a straight average. Straight average means it is just the average of the neighborhood. Okay, and weighted average means you are giving certain that you are doing averaging, but you are increasing the weights. Okay, but you have to remember that ultimately it should be within 0 to 55. Okay, you shouldn't cross that. You have to make the filter such a way that ultimately the whatever you do, the spatial intensity value will be less than will be between 0 to 55. Okay, so that's the way you have to do. Okay. Okay, so the useful thing is that the most useful thing is that re- it actually replaces the noise. Suppose why it replaces the noise? The answer is pretty simple. Oh, sorry, I didn't show this. Huh? Okay. Let's go this and we will try to look into this. Okay. Sorry. Okay, let's work it out. Okay. Okay, so let's work it out. What happens? Okay. So I think this will be done. Okay. So this is a simple 3 cross 3 neighborhood and the fxy. All of you are fine with this? Okay. This is a simple 3 cross 3 neighborhood in the fxy input image. Okay. Original image. And now you are applying a 3 cross smoothing filter. What happens? Okay. So it comes around 98.33. All the average of these pixels. Okay. And you replace this center pixel with 98.33 in the GXY. Okay. And this is the way you do for all the fxy's. Okay. So so this is a standard average. Okay. And then is okay. Okay. Then you can do something called weighted average also, as I said. Okay. Now something happens. See, when you are applying this kernel takes a 3 cross 3, right? Is it clear? So now if the center of the kernel is here, then you don't have any pixel values here, right? You can understand the problem? When I'm applying filters, you have to map the each of the center of the center of your mask to each of the pixels. So in this extreme rows of the image, right? If we map the kernel with the pixel, then these values are not there. Here, these values are not there. Okay. So how to do it? So we have to do some sort of things called zero padding. Okay. So we can apply the mask by padding this with zeros. Okay. Right. Or we can do the border padding. So we replace with the same values. We just push this here. We make one extra row. Okay. having the same values. So different things can be done. Okay, so this is the simple results you can also see in this, in a Gonzalez book, that spatial filters, smoothing, averaging effects, blurring. So if you see 3 cross 3 averaging, you see that it is okay. But if you do 9 cross 9 averaging, it's more blurring. If we do 15 cross 15 and 35 cross 13, it's blurring is more. Why? Why can you say? Larger kernel size is making more blur. Why? Why? Who can answer? Why larger kernel size is making more blurring? Who can answer this? So what it does, it now from the local averaging, it is now more to the global averaging, right? So ultimately, if we do the entire, if we take a kernel, suppose on discussion we take that this m cross n image is of the, that means is actually these kernels are all of the odd numbers of cells. Okay, so suppose take us, just for the sake of discussion, suppose m cross n is an odd number. Okay, so now if we take a kernel of m cross n, what will happen? So that's the largest kernel you can operate in the image. Okay, what will happen if we do the m cross n kernel on an image, and for each fxy we generate this gxy? What will happen? Ultimately, it will actually make a global average, right? Each pixel will replaced by the global average, which means that everything is same, right? Because global average for every pixel is same. Okay, so it will be all same, only one value will remain. That gxy will be an image where all pixels will have one value, because global average is constant. Now local average will differ depending on the locality where you're offering, because that is not the entire pixel. Okay, so it depends that how much, that means how much specific local information you want to keep. Okay, okay, right, and how much you want to push the local information to the global information. So normally that's why you don't increase because image information has a very valuable thing contained, very valuable information contained in the neighborhood. So you don't want to use larger kernels to lose the neighborhood, and you make more and more global decisions. Okay, so maybe in some algorithms you might require a global decision, so then might you require a larger kernel. Okay, but normally we'll see normally the kernels are smaller kernels, 3 cross 3 maximum, 5 cross 5. Okay, let's move on. So this is the weighted average. Okay, I think someone asked me, right? So what will happen, instead of 1 we go 2, 4, 2, something like this. Okay, okay, but why I did 1 by 16? Can anyone tell me? Instead of 1 by 9? Right. So because we have to keep it normalized within 255. So ultimately you can do it, but ultimately you have to normalize it. Okay. So this is called the weighted average. Okay. So I'm not moving. I will now move a little bit fast, because I think now the basic concepts are clear to all of you. Okay. Um, Now the second part. Okay. The first part we discussed about the pixels which are called the filters which are called linear filters. Okay, which do linear operations. But now we will discuss some of the filters which are based on ordered statistics. What that it means? Previously, if you see the filter, Okay, taken a cumulative operation. It is a function. The filter function is some linear operation over its neighborhood, and that value replaces the center pixel. Now what I do a ordering of the neighborhood. Instead of doing a linear operation over the neighborhood, I do a ordering of the neighborhood. Means, suppose max filter. Max filter means you replace the center pixel with the maximum value of its neighborhood. Mean filter, you replace the center pixel with the minimum value of the neighborhood. Median filter, we replace the center pixel by the median value of the neighborhood. So we actually ordered the neighborhood. Suppose this is a median filter. So we order the neighborhood. Ordering of, so there are, okay, so this is a, yeah, this is a neighborhood, though this is called as, this is shown as 4 cross 4, but actually this will be, normally we take a 3 cross 3 or 5 cross 4, whatever it is, okay? So we order the neighborhood and we see that 95 is the median, okay? So we replace all the pixels by 95, so replace the center pixel by 95. So those are the filters which are called order statistics based filters and also called nonlinear filters, unlike the linear filters, okay? So we don't do a linear operation, but we do a ordering of the neighborhood, and then we select the value based on the order, either mean, max, median, statistical. Actually, these are the statistical, what I can say, a statistical, the operation is done on the neighborhood, and that result replaces the center pixel, and that's why it's called a order statistics filtering. Okay, so am I clear to all of you? Am I clear to all of you?
Yes, yes, sir.
Good. So you can go with the median filter, which reduces salt and pepper noise and all these things. Okay, just wait. Just wait a second. Um, so this all you can just check that, and you can find the difference between averaging, median, filter, all this. So you see what happens is that, okay, in case of noisy image, okay, so this is a salt and pepper. This is an original image. This is a salt and pepper noise image, and you see the median filter. Median filter actually replaces the salt and pepper noise better than averaging filter. Because averaging filter, if the noises are very high, then averaging filter might not work, because then it will also incorporate noise. Okay, but median filter will select a median value which can be your desired signal, and where the noise can be on the two sides of the signal. Okay, and so the median value can be the clean signal, where the noise samples maybe, or the noise values maybe on the two sides of the signal. So that's why might be median filter can work better for the salt and pepper noise, because salt and pepper noise have both the type of distribution. Salt and pepper noise means you have black and white pixels coming randomly, which that as a noise in your image. So as black and white at the two extremes, maybe median filtering of intensity will be better in the case of salt and pepper noise. Okay, am I clear to all of you?
Yes, sir.
Okay, you should be very good in conceptual thoroughness. Okay, so sorry, so this part is over. Now I go to the second part of my lecture. Okay, I will skip some things. So this is also a PPT. You can just skip this, right? And it has some coding in Python. You can just go through that. You can just try these codes. in Python, and you can see what happens. We're not getting into all this. So, okay, this is what is the smoothing, and okay, so this is the mathematical. Sorry, I missed this. When you try to represent this filter operation in a mathematical form, this is the mathematical form. Okay, so who can interpret this equation, the entire equation? Who can interpret this equation? There's a little thing you have to just shift this a bit, because I don't know, because this needs to be shifted a bit here, then it will be good. Okay. Sorry. Gosh, there is something. Sorry. Okay. Now it looks good. Okay. So tell me, who can? Huh. Yeah, tell me. Yes. Hello. Yeah. Yeah. Who can explain that equation? Tell me. Yes. So what is this fx effect? What is this bound of s and t? And what is this wst? And what is this fx plus s and y plus t? I think you have answered it, but I don't know that how your friends are getting it. That's why I think that means you have answered it, but all of you are getting every component of the equation, right? That means I think we didn't have to explain this in 8th semester, but still, if you have any confusion, let me know. If anyone has any confusion on this equation, okay, I can explain it. Anyone? Any confusion? Anyone has any confusion on this? I'm not getting a response. Anyone? Yes, no, sir, no confusion. We're all fine. You're all fine with this equation? I can proceed to the next?
Yes, sir.
Okay, good. Fine. Okay. So I'm just skipping a bit on this. Non-linear, these are discussed, these are discussed. This you can just look into this, and probably Pavitra will also connect you on this. Okay, I'm just this. Okay, so now we'll go to the last part of this. So we discussed about the low pass filters, I think, right? What are the low pass filters? And now we discuss about the high pass filters. Okay. So high pass filters basically operates on the gradient operation. Okay. So what is a gradient operation? So this is a gradient operation in a one-dimensional space. Okay. So del f del x, which is the how the function f changes with x, where f only depends on x, is basically fx plus, actually it is fx plus delta minus fx, but in case of image, the delta is at least 1 pixel. You can always tell, hey, my delta is 2 pixel, which is called that means you know that it is called in the case of convolution kernels, we define a parameter. Okay, what is okay, that means what is the that means okay, that means how this kernel, okay, kernel moves across the image, and we can define the parameter 1, 2, depends on how it hops across the image. Okay, but in normal image filters, this delta is always 1. Okay, right? And this is the double derivative, derivative, which means that how the derivative of f changes with x. So del f del x is how f changes with x, and del 2f del x2 is how del f del x changes with x. And these are simple things we already know from 10 plus 2. That means our simple differential equations. Okay. Now I show you to these are again taken from Gonzalez. Okay, don't be very much. That means the where from where I can will get this is all from Gonzalez. Okay, all examples from Gonzalez. So what I show in the top is the intensity variation. Okay, is the intensity variation. Okay, so this is your x, and this is how the intensity changes. Okay, now if we do a derivative of this, what will happen? In this part, derivative is 0 because there is no change, right? Yes, yes or no? Okay. Right, and just here the derivative will just go negative because the value starts changing. So you just go negative, and then it again remains. That means the slope is the same. Okay, okay. So derivative. Uh, okay, is the maintains the same value 1 because the slope doesn't change. So derivative is constant here. Here derivative was 0, here derivative is constant, so you maintain the derivative. Okay, that means again you make here this with the derivative becomes 0. Okay, no change in the value, so again it's 0, right? And again it shoots up because here there is a rise in the derivative, again it becomes 0. Okay, so if we try to look into the second derivative, okay, if we try to look into the second derivative actually picks up here. Okay, second derivative picks up here. So you see that this here it picks up. So the changes in df dx it picks up. Okay, so it picks up here, it picks up here. Okay, right, it picks up here, right, and this is the way it picks up. So if you want to record a change in the intensity with, okay, that means how the intensity is changing with x. Okay, and based on that you want to take a decision, then a second derivative. Okay, and if you just want to record the intensity of x, right, it becomes a fast derivative. Okay, so this is the things which you can just understand what is the requirement of first and second derivative in the case of an information across one dimension. Okay, now this you have to, sorry, the equation is a little bit I don't know what happened. Gosh, this terms. Actually, I don't know. Actually, sorry. So you can understand this. I'm not getting into this. So this will be del 2. Yeah, it will be del 2 f del x2. Let me see. Oh my God. Okay, I will change the equation and send it back to you. Okay, this is there is some issue. Okay, well let us look into this part. That is the best part. Don't go into the upper part. That is the last equation. Del 2 f del x. So why is del 2 f? Because it is a f is now a function of both x and y. So del 2 f is actually del 2 f del x2 plus del 2 f del y2. So that's why it's a so this is a full neighborhood function. So which means that the center pixel is fxy, and if you want to do del 2 f, you have to operate fx plus 1y, fx minus 1y, fxy plus 1, fxy minus 1, and fxy, which is a cross tree kernel. These are the neighborhoods of your x and y. So these are called the Laplacian operators, which are basically based on if you see this minus 4xy. So how? Okay, so now give me now let's try to see that. Suppose this is my equation. Okay, suppose this is my equation. How I can define a kernel out of that? if this is my equation, what is the kernel? It's very simple, right? You look into here. So what you have? You have fx plus 1y is there, fx minus 1y is there. So fx plus 1y is there. So fx plus 1y is this, fx minus 1y is this. So these two are 1. Okay. fxy plus 1 and fxy minus 1. So this is fxy minus 1 and this is fx plus y, fxy plus 1. So these two are 1 and fxy is minus 4. So this is the, if this is the equation, then this is the kernel. Okay, this is the kernel. So you got this? This is the kernel. Okay, if this is the equation. Is it clear to all of you? How from the derivative equation you have generated the kernel? Is it clear to all of you? Right? And similarly, you can have the different variants of this. Okay. So it is just a more focus is given to the fxy. So you give -8. Okay. Here it's just the inverse kernel. Instead of this is 1, we make this minus, and this is 4, and this. So these are all Laplacian equations, which are nothing but the two-dimensional or the second order derivative of the second order derivative operations on the image. Okay, and these all kernel operations actually work. These Laplacian kernel operations actually sharpen. Why it sharpen? Because it will magnify. Why it will sharpen? Can you tell me? Just looking into the kernel, why this will sharpen? Why this kernel will sharpen? Sharpen the, why it is a high pass filter? High pass filter means it will sharpen those pixels which are pretty different from the neighborhood. Now, why this kernel will be, see, so if it is a high pass filter, then on those pixels where center pixel differs much more from the neighborhood, this kernel will generate a higher value. And for those pixels which are close to the neighborhood, this kernel will generate lower value. Now, can we appreciate that looking into this kernel? Can we appreciate that? Try to think on this. See what I'm trying to do. Suppose we assume that this center pixel is pretty close to neighborhood pixels. Maybe this 4 neighborhood pixels. What will happen? See, these neighborhood pixels will generate almost equivalent to 4 times of this particular center pixel, and you are subtracting 4 times of the center pixel, so it will be close to 0, assuming that these neighborhoods are pretty close to the center pixel. So your kernel value will be close to 0 or low if the center pixel is close to this neighborhood. Yes. Try to look into the maths. That means, are you okay with this? If the center pixel is closer to the neighborhood, this kernel operation will generate low value for the center pixel, right? And if the center pixel is pretty different from the neighborhood, then addition of the neighborhood and subtracting 4 times of the center pixel will generate a large value, because the center pixel is pretty different from the neighborhood. And so summation of the 4 neighborhoods with with the negative of the 4 times the center pixel will give a high value if center pixel is pretty different. And so that gxy will be pretty high. So this is a filter operation, and this will be the same for every other filters, okay? Every other kernels. So this particular filter will generate a high value for the center pixel, for which the center pixel differs largely with the neighborhood. And that's why it's called a high pass filter. And that's Laplacian second order high pass filter. Okay, is it clear to all of you?
Yes, sir.
Yes, sir.
Right. So just do the mathematics, I think it will be fine too. So I'm not getting into more on this. You can go to the codes and all these things. You can do much more operations, sharpening. All these are corners which will do the sharpening, and all. And these are called Roberts, Sobel, and all these things. These are the variants of the other high pass filters, which works on first order derivatives. Okay, and you can look into how this operates. Okay, these are all the Roberts, Sobel, Prewitt, all these corners. So, so, so I think for study, what we have to do is that. Okay, for study, what you have to do, you have to go through these two presentations. Okay, what I will just upload into classroom. With this, what you have to do, you have to also study the spatial filters, what is given in the book of Gonsalves. Okay, I have given the examples of Robert, Prewitt, Sobel, Laplacian, which you also go through the book, and you try to go through the simple way the kernel operates. Okay, and for the low pass filters, we have discussed in details of the low pass filters, the ordering filter, the linear filters, and the ordering based filters. Okay. In the next class, I think we will stop the discussion on spatial filtering here, and in the next class, we will try to discuss on the frequency domain informations, frequency domain filters, frequency information, and frequency domain filters. Okay, but before that, you should be very thorough with the image fundamentals as we discussed in the previous two class, and then the next two class on the spatial information and the spatial filters. Okay, so any questions? Anyone? Anyone of you have any questions on this? Okay, so if not, I will close the class. We will meet again again on next Monday, and I will be there in my office today from 1 p.m. to 4 p.m. Okay, so if anyone has any work from your batch, okay, you can come and meet me. Okay, so thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.